I think we're live. I think. Let me head over. All right. So, I think, yep, 12 seconds. All right, good. Looks like. Oop, pause that. All right. So I've got everything up here. All right. So let's see. Normally we start with our $10 and up questions. But before we get into that, I want to just take a moment to just thank all of you for all of your support. I haven't really made a vlog about this yet, but I have, for a while, I think I made a Patreon post about it, but a while ago we hit the $2,000 a month mark, which was just absolutely amazing. And as a result, I was able to quit my teaching job, which is just fantastic. I enjoy teaching, but I'm really excited to put more of my time into the videos, and I'm excited for what that means for the kind of videos that I can actually make. So very exciting times. All right, so on that note, let's get into some of these $10 questions here. All right, so William Morton was wondering what the quantum of heat would be. He sent a link to an article about calcium ions and using calcium ions to measure heat flow or something like that. It's kind of hard to know because the article was a bit vague, but I'm going to do my best to interpret it. So basically, what they were talking about in this article was that they somehow took the thermal energy, or what you might call heat, but we'll get into that in a sec, and sort of dumped it into the quantum spin of some of the particles that make up the calcium ion, and somehow that was a better way to measure or more efficiently use the energy, which is something we'll come back to at the end of this. But I want to clarify a couple things. First off, heat isn't really its own thing. So asking about what the quantum of heat is doesn't really make a whole lot of sense. Heat is what we might refer to as microscopic work, right? Work as in work and energy. And so basically, when we call something heat, what we're saying is that thermal energy is being transferred from one thing to another. And there are, three ways that can happen. You can do that through conduction. Basically, two things are in physical contact with each other and the heat transfers. I should say the energy transfers as heat. So thermodynamics is just littered with horrible language left over from like 1850, when we thought that heat was a fluid. We called it caloric, which is where the word calorie comes from. And so a lot of the language we use to describe things like heat and flow and that sort of thing is left over from when we thought that was a fluid. In fact, back then we thought everything was a fluid. But it makes talking about thermodynamics these days kind of difficult, but I'm doing my best here. So when energy is transferred between objects as heat, it can happen one of three ways: conduction from physical contact, convection, and what that means is we take advantage of some kind of fluid like the air to transfer heat more uniformly. And so a convection oven, for example, has like a bunch of fans in the back that circulate the heat around the cooking area. And then, of course, radiation, which is the least efficient way to transfer heat, but the only one available to the sun, which is how the sun heats the earth. And so the problem with thermal energy is that it's not very efficient, right? Once energy becomes thermal energy, and it usually does a little bit at least after any physical process, right? So we drop a ball and the ball hits the floor, and then eventually it stops because all of its energy has turned into thermal energy. And there are ways that we can take that thermal energy and kind of like get it back to use it for more work. In fact, that's what engines do, right? In internal combustion engines, take advantage of things like that to use heat to generate work, but they're not 100% efficient, right? We lose a little bit now and then eventually the energy just becomes so spread out that it's just no longer usable at all. And so that's kind of what we call a maximum entropy situation. And so what this article was talking about was how they managed to use this like calcium ion to transfer its thermal energy into the quantum spin states of the particles. And as a result, we can not only measure it more accurately, but also measure it, not measure it, but also use it more efficiently. So we can actually gain more of that lost energy back and make it more usable. I mean, you still have to obey the second law of thermodynamics. Entropy still has to go up, but um, we might be able to lose less of it in the future. We might be able to get more out of it, basically, which is kind of cool. But I think we're a long way off from using a single isolated calcium ion's energy. We're a long way off between that, right? And actually using this on a practical level. This, decades probably down the line, but it's kind of interesting, I guess. And so I mean, it's not quantum mechanics isn't really my thing. If you've been to the live streams before, you know that I do my best when I cover it in videos, but this this is a little. I think it's the best I can do with this particular article. So hopefully that is satisfactory for you, William. Okay, so let's see here. L.S. Greger wants to know. Says, okay, I was reading about pentaquarks. What are they, and why was there so much controversy over their discovery in 2003? All right, so the thing about quarks is that they come in groups, right? We can't ever have a single isolated quark. It's just not physically possible. And so they have to at least come in pairs, if not triplets, right? And those are the two sort of most common types of quark groups, right? We call the pairs, the two quark pairs, we call them mesons, and then we call the three quark triplets, we call them baryons, right? So, for example, a proton or a neutron is a three quark, it's a triplet. So it can have with particle with three quarks is bosons. No, bosons that's a whole other like category above this. Bosons are anything with a spin of 0, 1, 2, 3, 4, etc. Those don't necessarily have to be three quark triplets. There's a lot of lingo in particle physics. It's very easy to get these things mixed up. So we have mesons and baryons, right? So protons and neutrons are what we call baryons. They have three quarks in them. But 2 and 3 quark groups are not the only groups that we could have, right? There are groups of 4 and groups of 5 and so on. The more you have, though, the rarer it gets. And so we didn't expect to find groups of 5 quarks very readily, right? They're not going to just be available. And so we we expected to have a hard time finding them. And not only that, but also because two of the quarks inside the 5-quark group will tend to be quark-anti-quark pairs, and those have a tendency to cancel out. And so even if we manage to make a 5-quark group in a particle accelerator, it's probably not going to last very long. And even while it's there, that pair of particles, that quark anti-quark pair, is going to behave in such a way that it kind of hides the fact that we're looking at a 5-quark group. And so we had to be really, really critical of every single measurement that we made of something we thought was a pentaquark or a 5-quark group. And so it took us a while, right? So when they came out in 2003 and someone's like, we discovered a pentaquark, you still had to have a bunch of other scientists come in and look at the data and, peer review it and make sure everything looks okay. And then, do a couple more experiments here and there. And so we're still, even today, we're still trying to like decide whether or not these are what we actually found. And so I don't know if there's much controversy anymore, but controversy makes it sound like there's a huge argument over their existence, and there isn't. They definitely probably exist. Definitely probably. It sounds terrible. They probably exist. It's not something that a lot of people doubt. What we doubt is our ability to find them. And so that's sort of where the argument comes in, right? Not their existence, but whether or not we're actually looking at one. Okay, so Thomas asked a personal question a couple days ago, but I'm going to go out on a limb and guess that he'd prefer the science questions he asked today. So let's go with, I know I see you in the comments. So let's see here. If black holes have singularities and everything that falls into them ends up at the singularity, what makes the black hole grow? All right, so this is something we've talked about before, I think. But basically, there's two different things happening here with black holes, right? And so when we say something is a black hole, we refer to it as the black hole, we're usually talking about the event horizon, because that's the thing we can actually see. Whether or not there is a singularity is something that happens to actually be controversial. But the question was assuming there is, right? Assuming that everything collapses into this infinitely small point, which I think is ridiculous. But assuming that's the case, that will always be infinitely small, no density at all, ever, right? All right, sorry, infinite density all the time, no size at all, ever. Then we kind of have to refer to the event horizon as a size. And so it's the event horizon that actually expands. Now, this event horizon is not a physical thing. It's just a place, right? It's just a place in space. There is nothing actually there. It's just a sort of boundary, right? It's just a place in space where certain things happen on one side of it and different things happen on the other side, right? It's just a transition from one type of space to another, but it's just a place. And so that transition just occurs at a different place as the black hole grows, right? So as it collects mass, the curvature in that region of space grows. And because the curvature grows, the event horizon grows. The place where that transition takes place is further away from the singularity because the curvature is bigger. And so it's just something very important to keep in mind when you're talking about black holes and event horizons. It isn't this like physical boundary that you can like tap on or whatever. It's just a place. And so that particular transition happens differently when the black hole gets more mass. Okay, so let's see. Last $10 question here. What do you think about these 100 solar mass black holes astronomers believe they found? All right, so a little background. There's this gap, right, in between certain groups of black holes. So the way that black holes form and the way that they grow, they come in, there are sort of subcategories, right? There's stellar mass black holes, which are black holes that have just recently formed, I mean, cosmologically speaking, just recently formed from stars, large stars. And then there's the intermediate range black holes, where these smaller stellar mass black holes have maybe like collided and combined into slightly larger ones. And then, of course, there's the supermassive black holes, which likely formed way, way early in the universe and became the sort of collection point of matter for galaxies, which is why galaxies happen to have one of these things at the center. And so the controversy over 100 solar mass black holes that have the mass 100 times the sun, they theoretically shouldn't have existed. I should say hypothetically, because there's some things we're iffy on still, but there's some. Well, there was a proposal that there was this gap, right, between stellar mass black holes, which should really only go up to about 50 solar masses, and the intermediate stage, where after they're merging and stuff, those should start around 130 solar masses. And so somewhere between like, maybe 150. So somewhere between like 50 and 150 solar masses, there's this gap where we don't expect to find black holes, at least very often, because you can't form a black hole that large. And the smaller black holes haven't really had much of a chance to merge to make that size. And so we didn't expect to find black holes in that range, yet we did, right? We recently did find at least one in that range. And so there's a couple things happening here. So first off, there's an upper limit to how large, or how massive, I should say, how massive a star can be. Because of the way that fusion actually works. So there's a few things that happen. One, that if a stellar core forms that's so hot, right, that the radiation pressure being emitted out just makes the star blow up, right? So if gas tried to collapse into a very large star, like, I don't know, 200 solar masses or something, fusion would start in the core, and there would be so much energy release that it would go boom, right? And it would just blow up the star, like, immediately, supernova. That the star didn't even like exist for any length of time at all. And even below that, right, there's another limit we expect stars to hit first, which is sort of this upper limit where, the radiation being generated in the core through fusion, it isn't strong enough by itself to make the star explode, but the light rays, sorry, I should say the photons being generated during nuclear fusion are so energetic that they have enough energy to decay into like electron-positron pairs and stuff like that. So they can decay into particle pairs and become matter, at which point the star doesn't have enough radiation actually being emitted to hold itself up. And there's this sort of runaway collapse in the core, and the star explodes anyway. And so in that particular case, we expect that the upper limit on those cores, the cores that start generating particle-antiparticle pairs, that occurs at about 50 solar masses, give or take, for the core, right? Which, if the core is 50 solar masses, then the star is somewhere around like 150 solar masses, right? And so there's this upper limit on the mass of a star that would be 150 solar masses. And because of that, we expect its core to be about 50, and therefore the black hole that it eventually forms to be about 50 solar masses. And so that's sort of the upper limit on how big a black hole can form. And after that, you can't really get anything bigger without, mergers and like mass collection and accretion disks and stuff. And so since we found these 100 solar mass black holes, we've really only found them in globular clusters. This is really, really densely packed clusters of stars, and that kind of makes sense, actually. So this just comes down to scientists maybe not considering all the possibilities. And so once we actually discovered these things, we discovered these black holes, and they were in globular clusters, we were like, oh, well, yeah, I guess that makes sense. And so it was just sort of that realization that like somebody didn't think of something, and that happens from time to time. We're all human, right? And what we need to do is look at this data that we've got and be like, oh, right, I'm a dum-dum, and then just kind of like move on with your life. Adjust your view of the universe and move on. And so this is just one of those situations where we discovered these masses that didn't make a whole lot of sense. But then when we looked at where they were, these densely packed star clusters, we were like, oh, well, sure, I guess black hole mergers would probably be more common in those clusters. And then it all kind of was like a moot point. So on that note, we'll open it up to everybody else, and it looks like we have a very active chat here. And it looks like the new version of the live system, the live streaming system here, actually puts the chat next to my actual view of the live stream, which is so much more convenient than it was at before. It's probably the only improvement YouTube's made in the last 6 months that I approve of. But let's see here. I'm bitter. I don't know if you can tell. Let's see. Oh, apparently Tommy does want to know about the personal question. Let's see. The question was, what's my favorite Jimi Hendrix song? I'm not a huge fan of Jimi Hendrix. It's a little weird. The music's a little weird. But I do like 70s rock, and I think I would go with the song Fire, probably. The tempo is a little bit higher than his other songs, and so I probably listen to it more often. I like higher tempo songs, especially when I'm trying to get motivated on something like writing video scripts and stuff. Definitely higher tempo is the way to go. It's my first. Hi, Warren. Welcome to the live stream. I know that gained a lot of patrons in the last few months, so some of you might be new. Hopefully, you kind of get the hang of this. I have a good time, and most other people have a good time too. So, all right. So let's see. Is the fact that radiation is so inefficient at transferring heat the reason why stars last so long? Part of the reason, yeah, because there's a lot going on with a star, right? While the man, while the core generates typically like high energy gamma rays, those lose a lot of energy on their way out through the outer layers, and so in the process of losing all that energy, they lose it, and then the particles inside of the star heat up, right? Which is part of the reason the sun is so hot. And so by the time this energy actually gets to the surface, which happens maybe 50 or 60,000 years later, it takes a long time for this energy to actually get out of the sun because it doesn't go in a straight line. It just kind of jumps all over the place. And so eventually it gets to the surface, and the plasma, the particles on the surface, are at the surface temperature of the sun, which is, instead of the core temperature, which is millions of degrees, the surface temperature is only in the thousands, right? Which is why it's yellow. And so by the time it gets out there, they're basically just the surface is mostly just emitting visible light. There's some ultraviolet and there's a lot of infrared, but it's there's mostly visible light, right? The sun's solar spectrum peaks in the like yellowish green area, and so right in the middle of the visible spectrum. So the peak of the sun spectrum is visible, and that's because the photons have lost a lot of energy on their way out. And so the sun holds on to a lot of the energy that it actually creates. And then once the radiation finally leaks out, it doesn't leak out at a very large rate, at least as far as space is concerned. And so the only reason that we get a lot of energy from the sun is because the sun has a very large surface area. It's a very big thing, right? But any particular little patch on the sun is actually not emitting all that much energy. Radiation, again, is pretty inefficient. But even with that, like I was saying, it's the photons have already lost most of their energy on their way to the surface anyway, and then on top of that, radiation is inefficient, and they don't emit very quickly, and so both of those things together can contribute to what kind of energy the sun can hold on to. But I think the biggest reason that the sun lasts so long is because there's a lot of it, right? It might be losing, hundreds of millions of kilograms of mass every second, but it's got so much more mass than that it's going to last billions of years. It's not going to run out for a while. And so it's got that going for it. Radiation being inefficient is more an issue for things like the International Space Station, right? When you got a lot of things inside of it, electronics and people generating heat, you need to get that heat out of the chamber, because out of the station, because otherwise you're basically just going to cook everyone inside. And that can be tricky, since radiation is the only way they can get rid of the heat, and it's very inefficient. And so you've got to have these like heating coils and stuff, or heat dissipation coils and stuff. The kind of thing that you'd find, on like a computer processor, right? They got a heat sink. The space station has a really big heat sink that's got a lot of surface area in it, so that it can emit as much radiation as possible. All right, so let's see. So lots of heat questions today. So what is heat in a universe that does not have anything to transfer energy between it? Well, if it doesn't have anything to transfer energy, then it doesn't have any energy, which doesn't make a lot of sense. I mean, you can say it is physically possible for a universe to exist without matter and light in it. It'd be a pretty boring universe to just have empty space-time and that's it. But it is possible. I mean, the math allows for it. So that's possible. But space-time itself also has energy in it, and that energy can move around because even in an empty universe, space can expand. It'll expand at a perfectly steady pace, but it will expand, and so energy can move around. And so and a universe without a transfer of energy would be basically a universe that doesn't exist. It's just not it's not possible. Let's see. Yeah, a universe without a heat gradient is a dead universe, sure. But even in our universe, even when we sort of reach the end of all thermal gradients and it's the heat death, the universe is still going to continue to expand. There's still going to be more and more dark energy over time. And so we still got that. I mean, it's not moving from one place to another or anything, but it is there. And so I wouldn't want to live in that universe, but it is possible. All right, so let's see. I just listened to The Theory of Everything by Don Lincoln, but it was while driving, so lots of info. Sure, that can be tricky, trying to learn something while you're so bright. Trying to learn something while you're driving, it's easier to listen to maybe like audiobooks. I don't know, so you can just sort of drone it out in the background. But oh, there we go. Looks like the white balance on my webcam is being weird, or the auto exposure or something. But I didn't realize that he put out anything audio related. I'll have to go look at that and see what he had to say. He's got lots of good things to say about particle physics. He knows what he's doing. We all want to know what non-baryonic matter is. Well, how do I say this if it's not like super abstract? Because a lot of times definitions in particle physics revolve around numbers, right? Particularly quantum numbers. And so, for example, like we were saying earlier, a fermion is any particle that's got a spin of 1/2 or 3/2 or 5/2 or 7/2, any odd multiple of a half. And then a boson is spins of integer amount or whole number amounts, so 0, 1, 2, 3, etc. And then each of those have subcategories, right, where you can have things like leptons, which are like electrons and muons and stuff, and you can have quarks, and all of those things are fermions, right? And so then you can start to group these particles together. And as you group them together, particularly quarks, right? Any group of quarks is called a hadron. And then there are two major types of hadrons. There are mesons and baryons, right? So if some kind of matter is non-baryonic, that means it's probably made of mesons, right? I think a pion, meson. I think it's got two quarks. Man, no, maybe not. Zeta. They started naming them after like Greek letters, and I can't keep them all straight. It's just one of those things that I have to like look up because I don't work with particles very often. But I'm sure there's a whole list of mesons that we found in particle accelerators and stuff, and all of those things would be considered non-baryonic. They're not baryons. But technically, a baryon is something that has a baryon number of 1, I think. And so like there's all these weird abstract numbers that we keep track of with these particles, right? Baryon number, we keep track of. Strangeness is a thing that sort of keeps track of like how many strange quarks a particle has. And so there's a lot of ways we kind of quantify all of these things. And so as far as non-baryonic matter goes, I'm not sure there's a lot of interesting things I can say about it, in general. There are some specific examples of it that can get kind of interesting, but otherwise, like the general category, there isn't anything all that special about it. It's just kind of a nice, convenient category when we're trying to sort of classify matter that we find on the cosmic scale in the universe. All right. So, see, for those interested, boson is a force carrier. All right. So, Warren says that a boson is a force-carrying particle. Now, yes, those are examples of bosons, but they're not the only examples of bosons. There are plenty of bosons that are made of other particles, like quarks, for example, right? So if you are making a 3 or any odd number of quarks, like 3 or 5 or 7 or whatever, you're probably going to end up with a fermion, because 2 of the particles are going to make a whole, right? Their quarks are fermions, and so they're made of like half spin particles. They're half spin particles, and so you have a half, and half makes a whole, and then another half makes it another half, right? So it makes it a fermion. But if you've got 2 quarks, then the 2 half spins can come together to make a whole spin, at which point it's a boson, right? So meson particles are bosons, and they're not force carriers. They just happen to be bosons because they have a spin of 1 or 2 or whatever. Usually 1 or 0 if it's only 2 quarks. But it's just sort of a way for us to count things out. Now, the force carriers, which I will do a video on eventually. I'm in the process of teaching myself quantum field theory. I sort of know the basics. I knew enough to like make a couple videos about it, but I want to go deeper in some future videos and like really get into color charge on quarks and that sort of thing. But if I'm going to do that, I need to research so that I'm saying the right things and not giving anybody bogus information. And so bought a textbook, and I'm going to teach myself and then teach all of you. And so it's going to be a fun experience. All right. So let's see what else we got here. There are gaps between neutron stars and black holes. Maybe, right? And so we still have, anytime we give a number, like we're like, oh, well, the maximum mass of a neutron star is 3 solar masses, right? It's 3 solar masses with some error bars, right? There's always an error range. And so we don't know exactly where the boundary is, right? So we know that a neutron star will collapse on its own, under its own weight, somewhere around 3 solar masses, right? And then also somewhere around 3 solar masses, give or take, we know that a black hole will form. But if they're overlapping, right? If the ranges are overlapping, we can be fairly sure that there's no gap between them, right? But we don't actually see anything like this where there's an actual gap between the ranges. But even with an overlap like this, there's the possibility that there's a gap between the actual boundaries, at which point we have to start talking about things like quark stars. where the neutron star itself, made of neutrons, might not be able to hold itself up. But if it collapses a little bit and maybe the core compresses into a gluon soup, something like you might have seen in the early universe, then that might be a different kind of classification, a different kind of dead star, a stellar corpse, as they're usually called. And so while there's no clear gap between neutron stars and black holes, it might be possible to squeeze something narrow in there, depending on where the true numbers actually are. Our math doesn't really explain a black hole's interior. Well, that's not entirely accurate. When we get to a black hole's interior, the inside of an event horizon, the math predicts very strange things. But just because strange things are predicted, it doesn't make them not true, right? Just because things are strange, it doesn't mean that they're false. If quantum mechanics taught us anything, that's what it taught us, right? Just because it's weird doesn't mean that it's false. And so if you take that to the extreme, down to the singularity, that's definitely a math problem, right? So we're pretty sure that there isn't actually a singularity at the center of a black hole. That might be what the math predicts, but when we start to get to things like infinite density, when we get infinity in anything, we start to question whether or not the math is accurate. But we don't actually know where the line gets drawn, right? Where does general relativity stop being accurate? It's not anything we can verify because we can't see beyond the event horizon. There's no experiment that we can do to verify anything beyond the event horizon. But it is possible for general relativity to be accurately predicting things slightly inside the event horizon. Maybe not the singularity, but inside is a possibility. And so we don't draw the line at the event horizon because general relativity fails inside. We draw it at the event horizon because, practically speaking, we can't see inside of it. Where to actually draw the line for the model, we actually don't know. It might be the event horizon. It might be just outside of singularity. It could be anywhere in between. So we have to be careful when we make judgments like that. Let's see. How do you feel about people saying that an equation explains something versus that it just describes it? Well, scientific philosophy questions here. I think in this context, explains, the word explains and the word describes are kind of the same thing, right? If you want to look at a math equation and say that it can't explain something, then I don't think anything we ever do in science ever explains anything. And I think that might be a bad, a bad place to be when we're trying to approach science. And so we like to think that science is explaining things for us, that there's some cause and effect, right? Because of this, there's this, right? If this, then that. And I think math can do that, right? Ultimately, in order to know that math is correct, we have to do some kind of experiment to verify it, right? That's what science is, right? Science isn't about doing the math, it's about verifying things experimentally. So if we do the math and the math says, oh, this should be a thing because of this, and we do an experiment and that turns out to be true, then I have no problem saying that the math explained the thing. And I think it's okay, right? I mean, obviously we do have to be careful with language, but I think it's okay for math to explain something. If you want to get super pedantic, the person doing the math is using the math to explain something. But I don't know that that level of pedanticism is necessary here. So I think ultimately my answer to the question is I am totally comfortable saying that math explains things. Uh, then again, I'm a theoretical physicist, so I guess that shouldn't be too much of a surprise. Let's see here. Did you wear the Pink Floyd shirt because you stopped your teaching job, or is that just a coincidence? It's just a coincidence. I love this shirt. This is probably the most comfortable shirt that I own, and so I wear it all the time. And it shouldn't be that surprising that it ends up in my videos sometimes, and that it ends up in the live stream like this. Although maybe not the best choice against this black couch, but so be it. But I love this shirt. And so I try to wear it in videos when it's relevant to the topic, but it does show up occasionally when it's not. Just because I like the shirt so much. Let's see. Oh, welcome, Rudy. See, this is your first time too. Would be nice to have two chats, one for questions for Nick and one for the conversation. Maybe, but I think I can keep track of this. I got it over here on the side, and it's fine. I can sift through, right? It's not. I'm not letting the computer sift through for me. Let's see. There's not like. Let's see what kind of good questions we got in here. Let's see. Physics Girl did a couple of videos on LIGO. In it, they talk about Young's modulus and the idea that space itself is very non-ductile. So space is expanding but not bending. Well, again, this is sort of a language issue, right? You have to, when you're a scientist, you have to, or a science communicator at least, you have to try and decide whether or not a word means something different to you than it does to the people that you're trying to explain something to. And so I don't know that bending is such a bad word, although it has given rise to the whole like rubber sheet analogy, which is just terrible in my opinion. But I did watch the video, and I remember I remember Diana mentioning the Young's modulus thing. And sure, I don't know that I call it a Young's modulus, but yes. So you would say that space time itself has a kind of elastic property, right? And you could measure that as some kind of elastic modulus. When we refer to something as Young's modulus, it's usually specifically tensile stress, so things compressing or stretching out linearly. Space doesn't do that. It does that in 3 dimensions. And so it's more like a bulk modulus than a Young's modulus. These are different like subcategories. But yeah, so you could maybe find a number that looks kind of like a modulus from elasticity, which, by the way, modulus is just a fancy word for constant. So when somebody says Young's modulus or elastic modulus, they're just saying elastic constant. And so you could do something like that for space-time to maybe get an idea of what's happening. I don't know how useful it would actually be in Einstein's field equations or the Friedmann equations or anything like that, but it is something that we could do to maybe have, a way to connect general relativity to elasticity by analogy. It would be kind of interesting to see how that would work out. But gravitational waves are a little more complicated than, say, waves on a rubber sheet. So I don't know that I don't know for sure that it's possible, but if the lead scientist at LEGO is saying that it is, then he's probably done it before, and I think we can trust him. So just something to keep in mind. All right, let's see. Looking for your view videos in quantum chromodynamics. Right now, I think color charge is simply a bookkeeping math trick. Sure. Right now, it might seem like that. It might seem like a bookkeeping math trick, but there are a lot of things in physics that started out as a bookkeeping math trick and ended up being real physical things, right? So, for example, the whole like E equals HF quanta of light that Planck came up with back in 1900, like the actual year 1900, October, I think. Back when he came up with that, he came up with it as just a math trick to get a solution to some thermodynamic thing, a black body radiation. And so he came up with this thing and was like, it's just a math trick. It makes the math work out and we get an equation that matches our data. And so don't read too much into it. And then over the next few years, people started to read into it anyway. And it turned out that he accidentally stumbled on some huge, profound nature of the universe. And so that's something that happens after a while when we start to realize that the math, the bookkeeping trick explains things so well that it's basically blown all the alternatives out of the water. And at some point, you kind of just have to accept that this is probably the reality of the universe, right? Now, that doesn't mean that it will always happen. There are plenty of bookkeeping things that aren't the only method of solving problems, and there are other ones that are just as accurate, at which point you don't necessarily accept that that's the reality. For example, virtual particles, right? Virtual particles are a math trick that we use to more easily solve problems, but they're not the only way to solve the problems. There are other methods that don't require virtual particles, and they're just as accurate. They're just harder to do. And so at that point, you can probably conclude that virtual particles are probably not real things, which is, part of the reason that we call them virtual. So as far as that goes, right? Just because something's a math trick, it doesn't mean that it's not the reality of the situation, but it doesn't mean that it is either, right? We kind of have to figure it out as we go. Let's see. What does effective mean in effective stress energy tensor? We use that word a lot. And to give you a more concrete example, I'm going to just come back down. Instead of talking about general relativity, let's bring this back down to classical mechanics, orbital mechanics, for example, right? So a lot of times in orbital mechanics, there is some kind of gravitational potential, for example, right? And so the sun exerts a gravitational potential, and you could map out what a planet was going to do using that. But if the situation is a little more complicated, like you want to find a Lagrange point, for example, then you've got two objects like the sun and the earth, or the earth and the moon, right? And then you're trying to figure out what's happening to a third thing. What you need to explain how things are working is an effective potential, right? So not the actual physical potential energy or potential generated by these two objects, but an effective one that looks kind of like a potential, but isn't actually a potential. It's just a mathematical expression that can be used as a potential in the equations that you're doing, even though it isn't actually a potential. And so the same kind of thing goes for an effective stress energy tensor, right? There's only one kind of stress energy tensor, but sometimes you can make the math easier if you expand your definition of what the stress energy tensor is, and you use that in place of that tensor. Then it can simplify the math a little bit, but it's not actually the stress energy tensor. It's just a mathematical I don't want to say this. Can't think of the word. It's what we call it an effective one, because it acts like the stress energy tensor in the math, but isn't the actual stress energy tensor. And it's just there for mathematical convenience. It's not a real thing. Let's see. Going by Google, the largest neutron star is 2 solar masses, and the smallest black hole is 3.8 solar masses. Those numbers are not the theoretical possible numbers. Those numbers are the ones that we found, right? The actual examples of those objects, right? So the largest neutron, when you say the largest neutron star is 2 solar masses, what you're saying is the largest neutron star that we've ever seen is 2 solar masses, and the smallest black hole that we've ever seen is 3.8 solar masses. That doesn't mean that there aren't neutron stars that are bigger than 2 and that there aren't black holes that are smaller than 3.8. In fact, the math tells us that the boundary, the transition between a neutron star and a black hole is 3 solar masses, right? We just happen to have not found any in the gap, right? There isn't a theoretical gap. It's just an observational gap. Those are two very different things. Okay. Why do wormholes not have a horizon? Black holes do. Actually, wormholes should, as far as I know, should have an event horizon as well, right? They just happen to be connected to some, right? They're basically the entrance of a wormhole is still a black hole, right? It doesn't look like it would look in, say, like, Star Trek or something, right? A wormhole would be inside of a black hole, and so there would be an event horizon. You would go in, and then you find the specific spot, and it would lead you to another universe where there happens to be something we call a white hole, right? Where you would pop out the other side. If you could survive the G-forces inside the black hole, which you can't. But you would basically be particleized, right? You'd be just turned into subatomic particles, and your subatomic particles would make it into the other universe. But I don't think that's what we're going for when we go through one of these wormholes. But if you had a naked wormhole, that would be very strange, I think. All right. Let's see, we're running out of time here. Let's see. Question that keeps me up at night: our knowledge builds on itself. Do you think it is possible that all our knowledge is based on bad assumption? No, I don't, because knowledge doesn't just build on previous knowledge. It also builds on like actual observation of real events, right? So before experimentation was invented, which we usually credit that to Galileo, but Ibn al-Haytham was doing it like hundreds of years before that. We just don't have a record of it in the Western world. But somewhere around the year like 1000 AD, right? We started like actually doing experiments, right? And when we do experiments and we collect this data, that data actually means something. It's something concrete about the universe. And so I don't think that we're just building on assumptions, right? I mean, we start with an assumption. You have to start with some kind of assumption, some hypothesis, but you then have to verify it. And so, in the process of verifying it, we either throw out bad assumptions or we continue to use ones that appear to be good. And so, we don't build on the assumptions, we build on the experiments, the actual results, and those are the things that we actually keep. And so, we've been able to build a very good idea of how all the different sciences actually work, um, over the last few hundred years, in particular, since not only we've been doing experiments, but also experiments have been something that people don't get burned at the stake for. Um, so since we've been able to actually do these things and collect this data, we've made a lot of progress, um, in that area. And so I don't think that it's possible for everything to be wrong, right? And that there are obviously places that we have holes, things that we're not sure about, but they're really tiny holes, and we just sort of gradually fill them over time. Now, it is possible to forget things, right? So, uh, there are plenty of scientific, discoveries that come along, and like it's like, oh, this is the easier way to do something. Let's just stop doing it the old way. And then eventually, over time, we forget that the old way even existed. That is possible. For example, building the pyramids, right? Just because it would take us using all this fancy equipment like cranes and stuff to build the pyramids, it doesn't mean that people in ancient Egypt didn't know how to build pyramids another way. We just forgot how to do it that way because we came up with a better way to do it, right? A way that works faster and takes less people or whatever. And so, it is possible to forget knowledge, but I don't think it's possible to just build from bad assumptions because there's, actual science taking place. Um, well, let's see. What is the origin of the asylum persona? So the full on like Nick Lucy crazy guy. He's toned down a lot lately, but I think if I'm remembering this correctly, that basically when I first started making videos, I thought about what other people were doing, and it was everyone was like, "Oh, I'm gonna like teach you about this thing," and so I decided that I was gonna do that. I wanted to try doing that. I want to try explain something to a camera and ultimately people on the internet. And when I did that, right, I planned the whole thing out and I set it up, and then I got in front of the camera and I just went crazy, right? I got super extra excited and hyper about what I was talking about. It was very, very fun, right? And I was certainly still a little awkward, but I got super excited about it. And so at that point, uh, I tried to fight it for a little while, and none of these videos are available for anybody to watch. Some of them didn't even get uploaded, but um, I tried to calm it down to try and like be normal, and it just didn't work. I just felt super uncomfortable trying to like tone down my excitement, and so eventually I just embraced it. I was like, you know what? Let's just make it the whole theme of the show. And so that's sort of where that came from. And I took a while, right? You can go back and watch some older stuff, and I took a while to find the sweet spot, right? So there were times when I wasn't crazy enough, and then there were times when I was way too crazy for it to be educational at all. And so I eventually, honed in on the sweet spot, and I feel pretty comfortable with where it's at now, and I can like bring it down for harder topics and take it up for easier ones, and I think works out pretty well. The exuberant enthusiasm of what draws me in. That's good to know. I think that's true for a lot of Science of Silent viewers. I kind of found a niche of people who might, watch some other educational content, and maybe it's cool, but like it doesn't get, them excited or whatever. And so I think I found a niche, and I'm just gonna keep going with it. Let's see. Conversation there. Is there a way to calculate? We'll take maybe one or two more here. So, is there a way to calculate the G-force, the Newtonian G-forces? Well, hold on. Or a black hole event horizon. All right. So, first, you got to be careful about what we mean by G-force, right? I mean, there's certainly tidal forces happening inside of your body as you fall into a black hole, right? Now, there's no actual force, there's no gravitational force pulling you in. You're just following the straightest path in space-time. But because that path is speed dependent, if you go in feet first, your feet might be moving faster than your head is, at which point that's going to stretch you out, right? You're going to get stretched out or spaghettified. And that is going to result, that difference in motion between your head and your feet is going to result in tidal forces inside your body, right? And so we can calculate those forces, right? There aren't any forces actually, there aren't any like gravitational forces there, but we can calculate the forces inside of a body or inside of a metal rod that we drop in there or whatever you want to drop in. It would depend on the material. You could calculate those things, and it would be a number. You could get a force in newtons or pounds or whatever. But as far as like G forces, like accelerations, maybe like it's tough to do around a black hole because there really aren't. It's so far from our concept of Newtonian gravity that it's kind of hard to compare the two, right? I mean, we can make general relativity work in the Newtonian limit, as it's called, like down in normal ordinary gravity, like around planets and stars and stuff. But it doesn't really work the other way, and so we have to be really careful about what we take from general relativity and then use in classical mechanics. So we just have to be careful. As amazing as the thoroughness is in shows like PBS Spacetime, it often goes over my head, and I have a hard time keeping focused sometimes. Yeah, I think Matt's show, PBS Spacetime, is I mean, it's a show I get excited about because it's one of the few that actually like goes deep and can keep your attention. There are a lot of channels out there that go really deep into stuff, but then I end up falling asleep or something while I'm watching it. But it probably doesn't help that the only time I actually watch YouTube videos is at night between like midnight and 2 a.m. Because I'm working on my own stuff during the day. But I need something with some hype in it, and I think Matt can do that. Matt does a really good job of doing that. But he does have a tendency to talk about really, really complicated stuff sometimes, right? He knows a lot about particle physics, and so he can get into like quantum and like the Higgs boson and stuff, and he he can. I can understand how he might like lose some people along the way if he's just talking about uh, a bunch. He's using a bunch of like jargon words and stuff that can get a little and get a little heavy on your brain sometimes. But I think like overall he does a pretty good job. He keeps my attention anyway. And so I can get why somebody might have that opinion. Let's see. Never fallen asleep watching a silent video. Yeah, I don't know. There's the weird random like the fast and stuff. Like I don't know, the surprise things probably wake you up anyway, even if you did fall asleep. Although I do know people do fall asleep to my videos. It has happened before. People have commented about it, but it is kind of hard with this sudden like screaming that happens sometimes. But anyway, I think we're going to call it here when we got yeah, hour 11 minutes. It's about that time. Stuff getting stuck here. Yeah. All right. So let's see. I think we'll call it for today, and I will see you at the end of September, right? We for those of you who are new, we do this live stream. Well, it's 2 p.m. for me. It changes, but I post a little clock for it. But we do this every last Saturday of the month, right? So for September, that's going to be the 28th. Now, if something comes up in my life and I can't do it, I will let people know. I usually announce these things about a week in advance, and so you'll have some advance notice. But I typically do them on the last Saturday of every month, and so hopefully we will see a bunch of you next month. And thanks for coming, and hopefully we'll do this again. Let's see. Where are we?